Hello, welcome everyone to this Rambus Design Summit session. My name is John Ebley. I'm the VP of Product Marketing for our Buffer Chip Business Unit at Rambus. Today, I will be talking about DDR5 memory technology and how it enables the next generations of servers. So throughout my talk, you'll have access to your portal there. If you have questions, please do feel free to type in there, and we'll try to get those answered as quick as possible. So I'd like to start off by setting the backdrop for why new memory technologies are needed and why they are critical. So the ubiquitous use of mobile devices, the rise of IoT and sensors all around us, and the network capabilities to interconnect these with powerful back-end servers has led to an exponential rise in the data that needs to be processed. CPUs are the recipient of all this data. They receive this data, and they work to reduce this data down to the results, the insights, and suggestions that we've come to expect from our applications that really do improve our lives. In order to process this ever-growing amount of data and these very heavy data-intensive workloads efficiently, denser processors in the data center, as measured by the number of cores in the processor, are needed. So what this graph shows is how those number of cores have scaled with time. So if we look back 5 years ago in 2017, the average number of cores is roughly 10. And what we see is that in 5 years, that is roughly tripled to almost 30. And today you can get a processor with up to 64 cores, and we see a steady roadmap going forward. Now, as the core count increases, the memory bandwidth per CPU socket, as well as the memory capacity, must grow at a rate proportional to the core count increasing. So what that really means in a nutshell is that the capacity and the bandwidth needs to double approximately every 4 years. So when a memory standard, a new memory standard such as DDR5, will have a very long life of probably 10 plus years. So at the beginning of that standard, the ecosystem really needs to think about what are all the requirements that are going to be needed over that time period. So I wanted to start off with talking about those requirements, and I think if you keep those in mind, it will be instructive as I talk about what some of the key DDR5 advancements are. So on the previous slide, I talked about capacity and bandwidth being really two of the primary requirements. These both need to scale as the core count per processor scales. Next, if we think about the unit that the processor wants, what it's doing is it's replacing cache lines from main memory. So the access granularity, or how much memory it gets for every transaction, needs to stay constant at 64 bytes. The reliability of the interface and the DIMMs and the DRAMs must be the same or better as today. And what that means is that it needs to be able to do single error correct and dual error detect. And it also needs to be able to survive one of the DRAMs on the module going bad. Another key challenge, which leads to a key requirement, is that server performance can be limited if we do not control the amount of power that's being dissipated by the components that are within that server. Removing heat and controlling the temperature is very important. DIMMs are typically designed to stay within about a 15 watt per DIMM envelope, and that has remained relatively unchanged. And then finally, with advanced memory systems, there's a lot of training involved. And we need to keep that training time down when we start up a system as to not impact the boot time. Okay, so what we use in the server is what we call the DIMM form factor. And that's how these server bits are delivered to the CPU. This form factor provides both capacity and bandwidth by ganging a large number of DRAMs together. So if we look at this picture on the right, you'll see 20 DRAM. If it's a dual rank system, there'll be another 20 DRAM on the backside. So you have a total of 40 DRAM. The amount of capacity can be scaled further when CPUs support multiple DIMM slots per channel. And so this example on the left shows 2 DIMMs being populated per channel. Now, one downside to this parallelism is that the loads on the command and address and data signals get quite high, and that degrades the signal integrity and can degrade the bandwidth. So there's always this tension between capacity and bandwidth. So to try to break that tension and allow capacity to scale without impacting the bandwidth, there are special on-module memory interface chips that are used to improve the signal integrity. And the server DIMMs come in 2 different versions. The first, which is in the upper right-hand corner, is the registered DIMM. So this has a RCD, or a registering clock driver. And what it does is it takes the command and address signals and it provides multiple copies to the set of DRAM to reduce the load and allow the bandwidth to scale. The second type of server DIMM is the LRDIMM, or the load reduced DIMM. So what it adds to the RCD is a set of byte-wide data buffers that also buffer the data signals between the CPU and the DRAM. The RDIMM is well north of 90% of the market. And these 2 types of DIMM, RDIMM and LRDIMM, are unchanged from DDR4 to DDR5. So while the concept of RDIMM and the LRDIMM are unchanged from DDR4, there are significant changes in the configuration of the module itself. So let's first talk about the data channel configuration, which are the black lines in these figures. So in DDR4, there is a single memory interface channel, meaning for every transaction, all the data bits service that transaction. And it's a width of 8 bytes or 64 bits. And then there's an additional 8 bits of ECC protection for a total of 72 bits. The burst length of DDR4 DRAM is 8 clock phases per read-write transaction. So a single transaction will deliver 64 bytes of data, which is a cache line. So that's how DDR4 works. Now, when we move to DDR5, one of the changes in the DRAM is that the burst length has increased to 16 clock phases. And this is in order to increase the channel efficiency and keep the internal DRAM timing at an acceptable rate. So in order to maintain the access granularity of 64 bytes or a cache line, the DDR5 module is actually split into 2 independent channels, which are called channel A and channel B. What you'll now see is that one of these channels is 40 bits. So it's 32 bits of data plus 8 bits of ECC. We couldn't do only 4 bits of ECC because then that would not be able to achieve the SecDed requirement. So it was expanded to the next boundary of 4, which is 8 bits. So that gives more than enough bits to maintain the same ECC protection with a little bit of extra for storing metadata. And what you'll see is because of this 40 bits and 40 bits, there's actually 2 extra DRAM on a DDR5 RDIMM or LRDIMM. And in a dual rank system, there would be another 2 in the back for a total of 4. So there is a little bit extra overhead for DDR5. This additional channel per module not only satisfies the access granularity requirement, but it increases the parallelism of memory operations in the data sets that the CPU has at its disposal. All right, now I'd like to talk about the command address bus and the clock. So for DDR4, what you'll see is there's a single clock along with a single command address bit of 33 bits, which is running at half the data rate of the data bits. These 33 bits are function-specific bits and not terribly efficient. Now, since we have to go to 2 independent command channels or control planes for DDR5, the bus had to be, its efficiency had to be increased. So now it's split into an A bus and a B bus, each of 10 bits, and it's running at the same data rate as the data. And these aren't special function bits; they're general bits. And it's a packetized command and address, so it can use those pins much more efficiently. And finally, you'll see that there is still a single clock, so both of these channels are running at the same speed. And then the final point I want to just make is that if we look at the data rate, excuse me, for DDR4, it tops out at 3,200 megatransfers per second, whereas DDR5 supports all the way up to 8,400 megatransfers per second. And what you'll be seeing is that the intro rate of DDR5 is 4,800, which is a big 50% boost over the 3,200 and the life of DDR4. Okay, so I talked in the previous slide about some of the changes from DDR4 to DDR5. This table has a more comprehensive list of the changes and new features of both the DRAM and the module architecture. So we covered the speed, the channel architecture, the CA bus, and burst length in the previous slide. These changes together increase the bandwidth, increase the efficiency, and lower the loaded latency in the same module connector footprint as a DDR4. I next want to talk about capacity per module. So the way that the capacity per module primarily is increased is by increasing the density of the DRAM. So for DDR4, the largest single die package you could have was 16 gigabits. DDR5 starts at 16 gigabits and is defined to go up to 64 gigabits. So what that would allow is for the capacity of a DIMM to go, or a dual rank by 4 DIMM to go from 64 gigabytes up to 256 gigabytes. Another way to get extra capacity is to use DRAM that use 3D stacking technology. And so DDR5 takes the addressing scheme of DDR4 and increases it to allow for a 16 high stack as opposed to just an 8 high stack. Finally, I'd like to highlight that as we improve the performance, improve the bandwidth, if not thought about primarily, power can rise, and then that can cause problems. So power was a primary consideration for DDR5. So 2 key things I want to highlight there that lead to managing the power and allowing for higher power efficiency or bandwidth per watt. First of all, is that the VDD level was dropped from 1.2 volts to 1.1 volt. And then secondly, on the command address bus, the signaling type was changed from SSTL to PODL to be in common with the data bus. And PODL signaling has the advantage of burning no power when those pins are parked in a high state. Okay, so I would like to talk about some of the other significant changes in DDR5 by considering the module. So over here on the left is a DDR5 RDIMM. By considering this module in the context of the overall server as it looks today. So a typical server today is a dual socket server. So you see these two CPUs. And each of those CPUs has its own set of DIMMs, as well as PCIe slots. The DIMMs are powered by dedicated voltage regulators on the server motherboard running off of a common 12-volt rail. There is a baseboard management controller that can communicate with all the components of the motherboard through various interfaces. And then finally, there's an array of fans to manage the thermals of the server enclosure. Using this context, I will now discuss additional DDR features that enhance power delivery, system management, and telemetry to improve the overall server design and performance. So DDR5 introduces an on-module power management IC, or PMIC, that receives the 12-volt input directly at the module pins, and then it generates 5 distinct voltage levels that are needed by the various components on the DDR5 module. So this moves the real estate and the cost needed for the onboard memory voltage regulators that have to be designed for actually the maximum population case, and that's moved to each populated DIMM. So you're adding the cost of that power management, as you populate DIMMs. The other advantage of this power architecture is that it greatly reduces the problem of IR drop on the delivery network. So you're delivering a high voltage 12 volt to the module as opposed to trying to deliver 1 volt on the motherboard through the module connector onto the module. This provides tighter voltage tolerances for the sensitive components on the DIMM, which can then help achieve the higher performance that's needed. Okay, I next would like to highlight the system management bus. This bus is used heavily at initialization time to discover the DIMMs populated and to start the memory channel calibrations. And platforms today, this bus is based on the I2C interface running a little over 1 megahertz. In the DDR5 platforms, this bus will change to I3C and run at over 10x that speed, over 10 megahertz. So the DIMM is architected to support these higher speeds by introducing a I3C hub chip that is highlighted here on the left. On the target side, on the controller side, it communicates to the host, to the CPU or the baseboard management controller, and then on the target side, it talks to all the various components, the RCD, the PMIC, and the thermal sensors. And so what it essentially is doing is it's once again acting like a buffer or a redriver, so that the system only sees one load on the DIMM, and then all the various components are hidden behind that. So that helps enable this higher speed, and the increased speed of the bus will allow higher rates of polling and real-time control while the server is running. Just a couple other highlights on this I3C hub. It includes the serial presence detect function, which is, as the system's booting up, it reaches out to understand what kind of DIMMs are populated and all the various configuration that's needed for that DIMM. So it stores that non-volatile information. It also has its own internal thermal sensor that can be pulled as the server is operating. Okay, and then the final DIMM component I would like to highlight are the two satellite thermal sensor chips, which are connected to the I3C hub via the I3C interface. So along with the hub, which has its own internal temperature sensor, there are three spatially different data points from the DIMM that can be pulled, and this provides wealth of information to the server, such that the BMC or CPU can use this to manage the fans and potentially reduce the overall noise or increase the fan speed when needed. If the temperature does rise, it can increase the DRAM refresh rate to reduce the probability of error. And in a last resort, if it finds that it can't give enough fan to control the temperature, it can choose to throttle the bandwidth to reduce the thermal footprint. So in summary, DDR5 includes more intelligence on the DIMM itself via the 5 components that I've reviewed in the previous slide. So the RCD, the I3C hub, the PMIC, and the thermal sensor, and the DB. To continue to scale server performance as the number of CPU cores increase requires this more capable DIMM. This is really continuing a trend of trying to offload intelligence from the CPU and really placing it amongst the server components that can most efficiently do the required function. So I'd now like to switch gears a little bit. Now that we've talked about DDR5, we talked about the components, we talked about why they've been designed that way and the value it brings. I'd like to now highlight the product areas that Rambus specifically is participating in to enable the DDR5 ecosystem. So as I mentioned briefly, DDR5 will be introduced at a speed bin of 4,800 megatransfers per second. And we have announced the first RCD and DB working at these speeds using prototype silicon, actually back in 2017. So Rambus has been working on DDR5 for quite a while and had early silicon proof, learned from that, and we reached production with that product a little more than a year ago. In October, Rambus announced the industry's first RCD operating at 5,600 megatransfers per second. We call this sort of the second generation of DDR5. This is a 17% increase in bandwidth. And we've been able to achieve this while lowering the latency of our RCD, as well as reducing its power. And then I'd like to share some exciting news. We recently announced an expansion of our DDR5 portfolio beyond the RCD and DB signal integrity chips to include the I3C SPD hub and temperature sensor. As we discussed earlier, these chips enhance system management and thermal control of these next generation systems to enable the bandwidth improvements that are needed while improving the total cost of ownership. Both of these chips will be used in tandem with our RCD chip on server RDIMMs, and the I3C SPD hub is an important component for DDR5 client DIMMs, which include UDIMMs and SODIMMs for high-end PCs and notebooks. So to conclude, Rambus has a growing portfolio of solutions for DDR5 with speeds up to 5,600 megabits per second. And we are now able to support the SPD hub and TS. So we have a DDR5 server chipset, and we have a component, the SPD hub, that can also be used on client DIMMs. So I would like to thank you for your time, and I hope you found this session to be beneficial. Once again, feel free to ask questions in your chat window. I've been told that also that these slides are available for download within the system, as well as product briefs for the products that have been discussed here. I would also like to invite you and encourage you to continue attending our sessions at the Rambus Design Summit. The next one, which I'll also be participating in, is the Future of the Data Center Roundtable. So I hope to see you there. Thank you.